Hello, good afternoon. Um, Welcome to this third session. My name is Amit, and we have been talking about the course that is Introduction to Semiconductor Devices, uh, NOC 23E82. Um, this is the third problem solving session. We are in week 3, that is August 12. My name is Amit. I am a PhD scholar at ISC Bangalore, and in your chat box, you can see my email ID, my personal email ID, and also my YouTube channel on which I upload the sessions that we conduct here. So you may refer in case you miss a session or two, you can refer to it afterwards or for some other purposes that you might need. All right, so let us start. Just before starting, let's quickly do a overrun of the previous sessions that we have been doing. In the week 1, we had talked about material classification, that is primarily what makes material a metal, insulator, or semiconductor. We saw that we had zeroed in on the definition of conductivity, electrical conductivity, that is. Finally, we saw some basics of quantum mechanics, that is de-Broglie wavelength and Heisenberg uncertainty principle. Then we moved on. Then we solved the time independent Schrodinger equation for infinite quantum wells. So in that we saw there are symmetric and asymmetric quantum wells. If you recall, the quantum wells look something like this, right? So this is potential, you can say, so to speak, potential versus x. So this was 0 to L, and this was extending voltage infinity, something like this is the energy plot, right? And then we also saw that in case we have a potential that is a finite potential, something like this is not infinity. So a particle is coming, classically it cannot go on the other side of the barrier if energy is lower than the barrier, but quantum mechanically it can, and we saw the tunneling probability for this. Finally, we came back to the semiconductors and primarily about the origin of the band gap, where we saw that how the periodic potential is modeled into Ronick Penny, and then we saw the famous dispersion relation, that is the E energy versus K is the wave vector, if you recall. We saw the K as 2 pi by lambda, and EK relations we saw, also called the dispersion relations, right? So we saw all of that in the last class. And then finally we saw the electron excitation, that is that if you have a band gap in a semiconductor, this is the conduction band denoted by EC, and this is the valence band denoted by the the boundaries of conduction and valence band respectively. And then we saw that how to if you shine light of sufficient energy, an electron can go from here to here, and if it reaches the conduction band, it can cause the conduction. And same a few questions we saw also in the week 2. And then we looked at the very important concept called the effective mass, which is derived from a dispersion relation. A dispersion relation again is your EK, energy versus wave vector. And we saw that due to their curvature in conduction band, it's actually the bands are actually not flat, there's a curvature there, we saw that. And then due to that there is something called the effective mass. So in the last class also we have taught effective mass is effective mass is just contains all the information, all the quantum mechanical information of an electron, of such a system, in fact as a semiconductor lattice, right? And then we need not worry about quantum mechanical effects so much. We can simply apply our classical mechanics expressions like F equal to m times a, force equal to mass times acceleration. In that, mass is just effective mass, and rest everything remains the same. P square by 2m, p is momentum, energy is p square by 2m, where m is the effective mass, and so on. And then we saw that something called doping in a semiconductor, that is we deliberately introduce impurities. If it's a donor, it's called n-type, that means it releases electrons. If it's acceptor, that means that particular atom will accept some electrons and turn the semiconductor a p-type. And closely related concept was the Fermi level, which is the probability of finding probability where the Fermi function is half of an energy scale. We saw its position in the band gap, and we also saw that what's a non-degenerate semiconductor. Now this is an important definition. I'll just repeat. If this is EC and this is EV, now all the expression that we have been doing in this course, there's a value of EF. This is EF. So in order for all the expressions to be valid, EC minus EF has to be greater than 3 kT. Only when the semiconductor is non-degenerate. So this is the definition of non-degenerate semiconductor. Please remember this. And then we saw the carrier concentration, that is the electron and hole concentration, in terms of some constants Nc and Nv. These depend on the material. For silicon they are different, for germanium they are different, gallium arsenide they are different. Ni is the intrinsic concentration, we also saw that. And finally we saw that if we change the temperature of a doped semiconductor, it goes through 3 regimes. Yeah, for more details, as I told you, you can go through the previous sessions that we had conducted, or the lecture notes of Professor Nadesh. Right. So now, up until this point of time, okay, I will pause here. If you have any doubts or comments or any queries regarding the previous sessions that we had talked about, because maybe you did assignment, you could not figure out a problem, or any conceptual doubts, I'll pause a bit here, and then we'll move on. No? Okay, all right. We'll go ahead. So, up until this point of time, we have been talking about this, that an electron can be sent from valence band to conduction band. What will an electron do when it goes to the conduction band? Right. Semiconductors, as we talked about, they have conductivity. Conductivity means ability to conduct charge or carry current, right? Now, how does you carry current? You apply an external voltage. You see, this is a semiconductor slab that you see on your right, and you applied an external voltage. If a current flows, if large amount of current flows, we say it's a good conductor. If no current flows, it's a bad conductor or insulator, right? But if you zoom in at microscope level, something like this is going on. So this is the motion of an electron. Note that electron is moving in a lattice, right? So assume it's a silicon. So it's moving in assume it's a 2D lattice. So electron is moving in this lattice. These are atoms, and it has to interact with these atoms. And here is our electron in blue, right? So it will go here, it will interact with this, and then it can go there, it can go here, it will do a random motion. At non-zero temperature, electron will do a random motion. Overall, its position will not move forward, it will stay put. You can see that it's coming back to the original position. However, if you apply certain electric field, you can see and every arrow is shifted, every blue arrow is shifted slightly to the right, because sorry, this is for a hole, but you can imagine the electric field is in the opposite direction. QE force will be in the forward direction, and electron will have a net movement, some finite movement, some very small movement in the positive in this direction, right? And that is what you call drift, means flowing, going with the flow. In this case, the force is being provided by the electric field. This is the current that we define. J drift is your current density, so its units would be amperes per centimeter square. You might have noticed we express everything in centimeter square, so it's a nomenclature that we have been following in centimeter square. Q is the total charge, Vd is the drift velocity, that is the velocity of electron. Again, this is on an average. Remember, this is all probabilistic, eventually quantum mechanical. Here we don't care about that. How can we not care about that? Okay, so I'll come to that. So this Vd is the drift velocity, is directly proportional to electric field E, the applied field E, and the proportionality constant is mu, which is also known as the, what's mu? Can someone tell me? This fellow has a name. Vd directly proportional to E. Vd is your drift velocity. E is your electric field. This is your electric field. What is mu?
Mobility.
Mobility. Okay, very good. So mu is my mobility. I have a follow-up question. What is the difference between mobility and conductivity? Or is there a difference or dependence? All right, we'll come to that, but first let's talk a bit about the mobility. So the mobility term that you see here, as you can expect, it's dependent on something I told you. See, you can clearly understand if this lattice is very close, then the electron will keep on colliding very frequently and it cannot move forward. So the time taken between two consecutive collisions, right, is called mean free path. This tau is your mean free path of the electron. Here I am talking about the electron. Okay, so all the discussion, E is its charge, this is the effective mass. I told you we have done bothering about the quantum mechanical effects. So everything, everywhere you see M, it's the effective mass we're talking about. Okay, and finally, so you say Vd equal to mu E here, and you see this expression of drift, right? Okay, so this expression you might have seen. Can anyone tell what's Ohm's law? Ohm's law. Does anyone recall? Come on, it's high school physics. You must know.
G is equal to IR.
J equal to IR.
V is equal to IR.
V equal to IR. Okay.
Voltage directly proportional to current.
Yeah, voltage at the proportionality constant is R. R is dependent on the material property. So you must have heard R equal to rho L by A. This is the resistivity, L is the length, A is the cross section area. And on a more fundamental level, it's actually J equal to sigma E. J is again your current density, sigma is your conductivity, E is your electric field. So if you compare this expression, J equal to E is the electric field. So here I can say that sigma equal to N E mu. Let's compare with this. This is also Ohm's law. J equal to sigma E is also Ohm's law. J is the current density. So you can say I by A. Sigma is nothing but 1 over resistivity. Sigma equal to 1 over rho here. E can be related to V. V over D is E. V is the voltage. E is the electric field. Remember that. So you can clearly see, I told you how our sigma, this sigma is conductivity. How it's related to mobility? It's related like this. It's on your screen. Note, in this system I have considered only the electron. Same discussion can be held for holes also. Okay. And thus the total conductivity will come out to be Ne mu n plus Pe mu p. P stands for holes, that is. Okay. So that's how an electron, when it's reached the conduction band, it can contribute to the current. I am emphasizing it can, because it needs an external field. You see this, it needs some external field. Only then it can conduct current. It will not conduct current on its own. Just like a metal cannot conduct current on its own. The electrons are in motion, they are free to move, but someone has to tell the electron to move, right? So that's mobility. Now it's a very simple question. This is I am forgetting. This is called the dimension analysis, something like that. Okay. So it says that V equal to mu E for small electric fields. It's fields. The units of mobility are. So I mean, few of you might know that it's centimeter square per volt second. But how do we calculate that? This is, I'm just an exercise in that. So Vd equal to sigma mu E. Sorry. Okay. Vd is our velocity. The units of velocity are centimeter per second, meters per second, but as I told you in this course, the meters, centimeter is also unit of distance. Mu we don't know. E is electric field. So IE is electric field. So we know that electric field is, if you recall, del V over del X, right? This V is voltage or potential. Okay, so electric field units, which are, can anyone tell me the so V is volts and this is X is centimeters. So I can write into volts by centimeter. So mu's, you cross multiply, it will come out to be centimeter square over volt second. So so units of mu are centimeter square per volt second, which is this option. So usually such questions are asked in gate exam. So in gate exam sometimes, or this technique is very handy in option elimination. So sometimes when I was writing the gate exam, I did not know many concepts, or I was not strong, for instance, in thermodynamics or atomic and molecular physics. So but I could attempt some questions and gain some marks just by the trick of option elimination, because some options cannot be correct because the units are not matching. So it's a very handy tool just to check in questions as well as in your concepts, that okay, what is it, how is it related to field, how is it related to current. It's a good idea just to have this dimension analysis in mind. All right. This is a very straightforward exercise. Now we move on to a numerical based on the same concept. So this question says that a small concentration of minority carriers is injected into a homogeneous semiconductor crystal at one point. Okay, so let me draw a semiconductor. So this is my semiconductor. What I am doing is I am injecting something in this. What am I injecting? Small concentration of minority carriers. So minority carriers, what does it mean? So if it's an n type, so let's assume it's an n type carrier, n type semiconductor, right? Then I'm injecting some holes, because in n type electrons are majority and holes are the minority charge carriers. So I'm injecting some holes in this n type semiconductor. An electric field of 10 volts per centimeter is applied across the crystal. Okay, so this means this external electric field E is been given to me as 10 volts per centimeter, and this moves the minority carriers a distance of 1 centimeters in 20 microseconds. Okay, so how are the holes moving? I'll zoom in the picture. So a hole is moving in this direction because the field is here, and it says that it moves a distance of 1 centimeters in 20 seconds. So Vd equal to mu E, I know that. and we are required to find the mobility. All right. So what is Vd? Vd is, you can say that, delta x upon delta t. Mu we need to find. E is given as 10 volts per centimeter. What is delta x? Delta x is 1 cm over 20 seconds equal to mu into 10 volts per centimeter. All right.
20 microseconds.
Sorry, 20 microseconds. My bad. Sorry. Thank you. 20 microseconds. So mu will come out to be, so 1 over 200 microns. This is centimeter square per volt second. So 1 over 200 microns is 10 to the power 6. That's 10 to the power 3. So it will come out to be 5000 centimeter square per volt second. Micron, remember, is okay. So there is a confusion. This mu is mobility. Okay. And this mu is units. So this is 10 to the power minus 6. If you do the multiplication, comes out to be 5000 centimeter square per volt second. So this means these holes will be moving, will have a mobility of 5000 centimeter square per volt second. Now the question asks, what is the conductivity of this n-type semiconductor? Hole conductivity. So I can write sigma p equal to, remember the last formula, E p mu p. E is my hole charge, which is electronic charge. We know its value. This is 1.6 into 10 to the power minus 19 coulombs. Mu p we just calculated. This 5000 centimeter square per volt second. No, some number of holes are injected. Let's call them P naught. Okay, so if P naught was given to us, we could put here and we find the conductivity of this n-type semiconductor. We'll see in fact today's session itself, and if you have gone through the week 3 lectures, we are talking about injection of carriers. So in this class we will also see how they behave. This is a fairly simple exercise. In this, just to summarize, a drift current is something that happens when you apply an external electric field. So it's very important that note that this field has to be external. So when you apply an external electric field, the electrons which are in conduction band will move, right, opposite to the electric field, and if there are holes, they will move in direction of the electric field, because electron is a negative charge, hole is supposed to be a positive charge. And the mobility, mobility is inherently related. If you see in here, E tau by m effective is a material property. Tau is also material property, and E is a universal constant. So mu, or the mobility, is effectively a material property. You cannot tinker too much with it. All right. So I'll pause here. Any doubts or questions regarding the drift current or the phenomena of drift in semiconductors? All right. Okay, we'll go ahead. So this was not part of the question, this thing. I just felt it's important to add here. Okay, now we'll move on to our next set of problems. Okay, so let's read this problem. It's a gate problem. So it says that energy band diagram of a p-type semiconductor bar of length L under equilibrium condition is shown in this figure. So this is a figure. So this is a p-type semiconductor and its length has been given L. All right, it's under equilibrium. So how do we say it's under equilibrium? The question itself answers that. The Fermi energy level is constant. You see the EF dotted line, this is constant. So any semiconductor that is at equilibrium, EF has to be constant. Otherwise, if EF is sloped, there will be a, the slope, or it's not same at two levels. This means electron probability is different, and the electrons from the higher region will travel to where there are lower electrons. EF will again become constant. So that's a fact of life. It's just like Professor Naresh mentions that in a water tank, however you can tilt your water tank or your bucket, the level has to remain flat. Same thing goes with EF in equilibrium. Remember, this is in equilibrium. Okay, next it says that the valence band EV is sloped since doping is non-uniform along the bar. So here the doping is non-uniform. You can see we saw in the last session that if EV and EF are close, this means a material is highly doped with acceptors. If EF is far apart, or EF is at the center or is equal to EI, this means it's intrinsic. So the more closer EF moves to EV, this means the higher is the doping. Okay, so here you can see on your left side where Z equal to 0, the doping is low, right? So I can denote the doping as like this. So here the dopings is low, very spaced apart. Here the doping is higher, so you can clearly see the difference in density. This is just for pictorial purpose, right? So these are the dopants, acceptor type dopants in this case. Okay, the questions ask the difference between the energy levels of the valence band and the two edges of the bar is delta. So you can see that the energy difference here is given as delta. Question asks the charge of electron is q and the magnitude of electric field developed inside this semiconductor bar is. So there's an electric field. We'll see how it comes. It's also shown in the lectures. I'll just quickly go through that how it arises even. Okay, so this is the problem that is given to us. We need to find the electric field here. So again, as the question says, is it at equilibrium? Yes, it's at equilibrium. Why? Because we saw that EF is flat. So the answer is yes, EF is flat. Second, is doping uniform? The question says that doping is non-uniform. Why I'm writing these questions even though the question itself said that? I'm writing this because whenever you encounter such problems, always ask yourself these two things. Whenever you see any Venn diagram in which you see a slope in it, so just be careful and just be careful. Excuse me, just a second. Yeah, ask yourself these two questions and then you will be in a better position to approach the problem. Okay, so in this the question itself was given, but I told you why it's non-uniform, because this here the doping is higher. In the last slide we saw that. Okay, now let's go ahead. So we know that force F is minus del U over del X. This U is your potential energy. Okay, very good. And force we know is minus QE. Why minus QE? Remember, we are talking about holes here. All right, and electron charge was given to us as Q, so whole charge will be minus Q. Okay, so force equal to minus Q into E. What is this E? E is the electric field across this, right? Because you can see that there is a difference in potential energy between Z equal to 0 and Z equal to L. Hence there will be an electric field. Or an alternate way of remembering this, if you see any of the bands is not flat, conduction band or valence band, this means there's an electric field. If EV is not flat, that means there's a field for holes. If EC is not flat, that means there is a field for electrons. All right. So F equal to minus QE equal to minus del U over del X. Very good. Sorry about that. Okay. So now let's solve it. So U. So I can now write is as minus minus gets cancelled. So I can write electric field as 1 over Q delta U over delta X. This is I'm just integrating it, you can say. So it comes out to be, this means U at L at this edge, at the right edge, minus U at 0 over L minus 0. So what is UL? UL is the difference between them is given to be delta. So delta by L. So electric field has come out to be 1 over Q delta by L. So we put our option 1 over Q delta by L, this one, or delta by QL, first option. Okay, so it's a straightforward exercise. The only thing you need to recall here is this is actually the basics that I had talked about here, but this is an expression that you see in your lecture slides, so you can directly remember that it's 1 over Q del EV over del X or del EC over del X. So whichever band you're talking about, it's associated to that. All right. So I'll again pause here. Any questions or comments? Please go ahead. Okay, this is just a direct application of the whatever was taught in the course. Even in the lectures, you can see there are some examples which professor solves. So this is similar to that. Okay. Again, a very similar problem as to before. So in this, the question says that a silicon sample maintained at 300 K, so it is not at room at room temperature, is characterized by band energy diagram as shown in figure 2. So this is the band diagram that you see. So here you can clearly see that EC is also not flat, EF is also not flat. Sorry, EV is also not flat. Now answer the following questions by choosing the correct diagram. Okay, consider EF as the reference energy level. So EF, the Fermi level you see, is flat. So the question says, do equilibrium conditions prevail? Yes, they prevail. The system is in equilibrium. Why? Because EF is flat. So EF is flat. So first question is yes. Why? Because EF is flat. EF is flat in x direction, right? In this direction you can see EF is not changing, so the answer would be this option. Yes, because Fermi level EF is constant along x. We'll see a problem if time permits today, where EF is not flat, and then how do you see? But just like I told, it's a good check to see whether it's sorry, whether it's in equilibrium or not. So what's the second check, if you recall? Sorry, I'll do it here. The second check that we had done was, is the doping uniform or not? Doping is uniform or not? So what do you think? In this, for this semiconductor, for this silicon sample, is the doping uniform in this sample? Come on, respond. It's a simple exercise. I'll give you a hint. So when EF is approaching EC, this means it's n type. More and more n type. N type increases. If EF approaches EV, its p type characteristic increases. Now tell me what type of this okay, let's break it down. At L equal to 0, at x equal to 0, what is this? Is this n type or p type, this semiconductor? Tell me this. Come on, go ahead. It's fine, even if you're wrong. Don't be shy. Anyone?
N type.
N type. Very good. It is N type. Why? Because as we see that EF is in fact very, it's even touching, right? So actually here it's a degenerate semiconductor. Remember we have talked about the distance of 3 kt. It's touching, so it's not even 3 kt, but it's N type. It's correct. So here it's N type. On the right side, if you see, EF is touching EV, so it's p type. So you can see that, you can just imagine like this. So this is silicon semiconductor. So what I am doing is, I am doping on the left side as N type. So what is N type? So let's say I'm doping with phosphorus. So this is a silicon semiconductor, silicon sample. On the left side I'm doping with phosphorus, and then phosphorus gradually decreases. Here it's undoped in the center. This is undoped. On the right side it's heavily doped with boron. Here it's mildly boron. Here also it's mildly phosphorus. Boron is a p type, so this becomes p type, this side becomes N type. So this is how this sample is being made. On the left side you dope with p, you gradually reduce the N, you gradually reduce the phosphorus, and then in the center it's undoped. At this point, at L by 2, it's undoped. You can see EF is equally spaced from EC and EV. Okay, so doping is not uniform in the semiconductor. In fact, it changes from heavily N type, then mildly N type, to undoped, to mild p type, and then heavily p type. So sometimes these kind of questions can be asked. So this is just you can remember that. Okay, now the next question is asked is that, so what is the electric field? Fine, we have already we remember the formula, and this is from your lecture slides. So 1 over q del EC over del x. So we can simply say, so now we just have to see what is the change in either EC with respect to L. So you can see that EC level, so let's say this is the reference level, right? So what I'm going to write is EC at x equal to L minus EC at x equal to 0 divided by L minus 0, right? I'm just writing DEC as delta EC. This will be, so now I just have to find the value of EC at x equal to L. Remember, EF I can take as reference. So here this thing is my complete band gap on x equal to L. Okay, I'll denote with the blue color. So here this thing is my complete band gap, and this is nothing but my EG. Okay, so now I can write, now this term is nothing but EG. Let's now look at what is the value of EC at x equal to 0. EC at x equal to 0 at this point, you see this is exactly at EF. So here this gap is 0. So here this gap is 0. Okay, so what will be the final answer then? You can just plug these values. So it will be So Eg for silicon, can somebody tell me the Eg for silicon? Eg is the band gap, by the way. What's the band gap of silicon? By now you must.
1.12.
Yeah. For gallium arsenide,
0.4.
for silicon is, what did you say? I forgot. 1.12.
12.
Okay, I always forget the second term. For gallium arsenide,
Is it 0.4?
it's 1.4 if I recall correctly.
Oh,
And there's a germanium also. That fellow I think is 0.7. I am sure about silicon and gallium arsenide. Germanium I am not, it's usually not encountered in my work, so I don't recall. So just I'm sure about this. Just please confirm this. Okay, this might be wrong, but just please confirm. Try to remember these values. Okay, as I told you, problem they are given, but when you're trying to analyze something, right, these are good checks. All right. Okay, so you find out that so it's a constant. You see, electric field is a constant. It's a positive constant. Eg by QL. Eg is positive. Q electronic charge. This is 1.6 E minus 19, and this is L, which is again a constant. So Eg is a constant. Then mean option A is correct. So you can say that this value is nothing but Eg by QL. This value, this level. Okay, now let's go ahead. So now the problem is asking us to plot the kinetic energy of electrons and holes. Okay, so let's do that. So how do we approach this problem? First of all, you can see that electron as well as holes, right, will see the electric field, because EC is also meant and EV is also meant. The electric field magnitude we saw in the last problem, which is here, EG over QL. So both will see, right, and electric field is on the positive side. So I'll denote it something like this. Let me use a different color, blue. So this is the E in this direction. Okay, now what's going to happen is that if there's an electric field, so if there's an electron, it will feel a force, right, F equal to QE, but it will, since electron is negatively charged, it will feel a force in this direction. Or you can see, just imagine an electron that is here. Okay, an electron that is here, right? So I should not write there. 1 second, sorry about that. Okay, so let's just focus only on the electrons, let's say. Okay, so let's try to analyze what will happen to an electron. So an electron, which is, you can just simply assume that electron will roll down this, something like this. So when it reaches on this end, it will have some kinetic energy. It's a very simple way of understanding, because electron is feeling a force in the negative x direction, right? So the electron will gain some energy, kinetic energy, by the time it moves from x equal to L to x equal to 0. We'll write it. So electron will gain some energy as it moves in negative x direction due to the built-in electric field. The electric field that we have calculated in the last slide is called the built-in electric field, because it's not external. Please be careful, this is not an external field, this is the internal electric field due to the doping, right? So electron will gain some kinetic energy, but at this point the kinetic energy will be 0, right? At this end it would have gained some kinetic energy, right? So you can see that at x equal to 0 the electron should have some kinetic energy, and at this point it should not have. So this is the correct option, and the opposite is true for hole, you can see. So when a hole is here, so it will feel a positive, it will feel a force in the positive x direction, and by the time it moves to x equal to L, it will have gained some kinetic energy. So at x equal to L, hole will have kinetic energy while electron will have 0. It's a simple way of understanding. Okay, or the other way you can say is the total mechanical energy has to be balanced, kinetic energy plus potential energy, right? So here the potential, because remember we have taken EF as the reference level, so here an electron which is here has potential energy equal to 0, right? But it has some potential energy here which is equal to Eg, which we saw in the last slide. So if it has potential energy here and potential energy is 0, then all the potential energy while coming from here to here must go into the kinetic energy, right? So at x equal to 0, electron should have some kinetic energy. And the same argument, opposite argument, is true for hole. All right, I discussed only for the electron here, but for the hole is also true. It's not gone anywhere. Okay, so we are done with this part for now. That is the non-flat electron conduction bands. Okay, so again I'll pause for a bit here. If you have any doubts in mobility or these band structures which are not flat, please feel free to ask. All right, if there are no comments, then we'll go ahead. Okay, so as we started today's class with something called a drift current, I told you that if there is some electrons in a conduction band, that itself will not carry some current. We have to apply an electric field. There's one more phenomena which can cause for electrons to flow. That is diffusion. So diffusion is a phenomena which you encounter in our daily life. For instance, if something is being cooked in the kitchen, right, and you are sitting 2 rooms away, you can smell that. That's due to diffusion, because the concentration of those the food is high in the kitchen and diffuses to your room. That's diffusion. It always moves from higher concentration to lower concentration. Anything which moves from higher concentration to lower concentration. Concentration is usually, in this course we are measuring it cm minus 3 per centimeter cube. This is how we are measuring the concentration. Dopants are measured, like atoms are measured per centimeter cube and everything like that. Okay, so let's see. So this is on your screen. So to your left you see a semiconductor, let's say silicon. So you can see that on the left side it's highly doped with Nd, that's dopants. So it's highly doped on this side. Here it's low doped. So what's going to happen is, on your left side we will have a higher amount of electrons. On the right side we'll have low amount of electrons. This means there is a gradient in concentration of electrons. Left has high amount of electrons, right has low. What's going to happen, the electrons will flow from left to right. And this diagram we saw just in the previous problem, that since the electron concentration is high here, EF has to be close to EC. We saw that. And the electron concentration is far on this side, so EF will be slightly far away from EC. Again, it will still be above the intrinsic level. Why still above intrinsic level? Because this is still n-type dope. So EF is still be above EF. EI, you see this this is EI. This is EI, intrinsic energy level, or the midpoint. This is EV and this is EC. The blue line is EF. Okay, and you can also see that EV is also tilted. That makes sense because band gap has to remain constant. The material inherently remains silicon only. Let's assume it's silicon. Okay, so this will remain to be 1.1 EV. Okay, so that's the band diagram. Fine, good, but that's not the complete picture. I need to know what's the current due to this movement of electrons, because remember there are higher number of electrons here, low here. So if the electron is moving, there must be some current, right? And that's called the diffusion current. So you can clearly understand J and diffusion is the again density of current density. Units will be amperes per centimeter square. Diff stands for diffusion, is proportional to the electronic charge naturally, and the concentration gradient. N is the number of electrons and x is the direction. So assume this to be the x direction, which is seen here, right? So this is dependent on that. If you remove the constant, if you remove the proportionality constant, the dn, the diffusion constant, comes into the picture. This is very similar to what we saw mu n, the mobility of electrons we saw in the first 2 slides today, right? Similar picture is true for holes, just that negative sign comes because of the charge is opposite in polarity, and dn becomes dp, n becomes p. So this is fairly straightforward. There's nothing much that is happening here, right? Let's apply this understanding now to a problem. What does this say? This looks a very long problem, very complex, but it's you read it word by word and it's very straightforward. Question says, consider hypothetical semiconductor subjected to an electric field. This is some semiconductor and this is subjected to electric field. This means this field is external now. This field is external. Okay, with a non-uniform carrier concentration. So these are the carrier concentrations that has been shown. In this, electric field is assumed to be the x direction. So this is the x direction. I'll draw it here. This is your x-axis. Okay, along with the carrier gradient nx and px decrease with increasing x. So you can see the electron concentration nx gets decreases as x increases. Similar goes for p, the hole concentration. Okay. The problem says that find the correct figure, direction of hole flow and hole current. Okay, so we have to find in which direction of hole flow. That's the first problem. Second problem is hole current under the drift and diffusion regime. Okay, so it's diffusion as well as drift. Let's first focus only on the drift. Okay, so if you recall, drift, I'll do it with a black pen because the diagrams here are in black. Let's focus on drift for now. So drift we know is in due to E external, right? So E external here is in the positive x direction, and we are talking about holes here. So since E external is in positive x, this implies hole will drift in positive x. Very simple, because force equal to q times E, and hole is positively charged, E external in this case. So hole will drift towards the positive x direction. So drift, this is the phi p, that is symbol you see is for hole drifting, right? They should move towards the right. So hole is drifting towards the right, so this option is correct. This may be correct, this is wrong. So here hole is drifting to the left. Okay, and if hole is drifting to the right, this means hole current will also be to the right. Hole current is also in positive x, because hole is positively charged. If the hole is going towards right, that means hole current will also be towards the right. Okay, so hole current will also be towards the left. This is wrong, because the direction of hole traveling and current has to be the same. So either B or C is the option. Okay, now let's talk about the diffusion. I'll choose the blue color. So diffusion, what's happening? So we have, for that we have to write the expression for diffusion, which is, this is a hole, remember. So E dp over dx. So I can write that jp is minus E dp dou p over dx. This is for diffusion, remember. This is diffusion. Okay, so E is a constant 1.6 E19, dp is a positive constant, del p over del x is negative because px is reducing. Please see that since px is reducing, del p over del x will also be negative. So this quantity will turn out to be positive. So jp has to be in the positive x direction. Okay, so which happens to be this, then option B is correct. Let's also think about the direction of the holes. Okay, so just see that here the holes are more on your left, on the right the holes are low because the concentration is decreasing. So here there are more holes, on the right side there are less holes. So the holes will go from this direction to this direction, and the direction will be positive. So again this option is correct. So that completes the analysis of this problem. What we saw in this case is that, okay, just let me say this. So if I remove E external, there will be no drift. Please remember that. There will be diffusion but no drift. This E external is causing the drift, right? In future problems, in some analysis today, if time permits, we'll see where the drift is not there because we don't have any external electric field. Well, diffusion can still be there. So these are independent processes. These two are not dependent on each other. Please remember that. Drift can exist independent of diffusion. Diffusion can exist independent of drift. Right? Please keep that in mind. Right? Okay, so then what is the total current? So I just told you there are two independent mechanisms, the drift and diffusion. Jn stands for total electron current. Right? And what will it be? So drift we saw was n e mu n e. This is E external actually. I should write it. This E, when I mean this is E external. Okay, and plus we saw the diffusion current is E dn dou n over dou x. This is the diffusion expression that we saw, right? Similar goes for P. So everything is changed. If you recall, the sign was different. That's it. Nothing else changes. Everything else remains the same. What is the total current then in the system? Remember, in a semiconductor, someone in the first class itself had mentioned that semiconductor, both electrons and holes can conduct. So total current in this case would be Gn plus Jp. So this, what do I mean by total? This is the in the semiconductor. So electrons as well as holes can contribute to the current. Usually when we dope it extrinsically, only one of these components is dominant. We'll see, you'll see in the future lectures that only one of these components is dominant. When we come to diode and other devices, we'll see that. But for now, this is the complete picture. So this slide just contains all the information that you need to know about the current in a semiconductor, right? Now just please remember that here only one external stimulus is there, that is the electric field. Nothing else external is there. All right, okay. So that's it. Now very closely related to that is something called the Einstein equation. So we see two constants here, mu and d, the mobility and the diffusion, right? How are they related? They're related by something called the Einstein expression. So this is the total, consider only the electrons in this case, same discussion will be true for holes. So this is the total current, right? If you don't have any equilibrium, if you an equilibrium, for example, this system is at equilibrium where Jn is 0, right? Okay, I should have mentioned that this E need not always, I was wrong in this, so sorry about that. This E need not always be external. Sorry, in that problem that was external, in the first problem we solved, this need not always be external. So even if there is some built-in electric field, the electrons can drift, we saw that. Okay, so I just, sorry for the confusion there. This E can be internal or external. Okay, right, at equilibrium, this means you are not so there cannot be any current. If a silicon semiconductor is sitting, right, it cannot conduct, it cannot carry current, right? Otherwise it can, we can just take energy out of it without any input. That will violate the thermodynamics laws. All right, so if I put Jn equal to 0, right, then this expression has to become equal to 0. Now we just need to find what is 2n over dx, right? And this is the expression for n, the electron concentration from your first or second lecture, right? Now I'll just differentiate it with respect to x. So this will be nc, this term will remain the same, ef minus ec over kt times, I'll differentiate what is inside, so that will become minus 1 over kt del ec over del x. This is nothing but n again, the first term you see. So this turns out to be n over kt minus n over kt del ec over del x. Now if you recall, del ec over del x is nothing but qe. All right, you put this here, so this will come out to be n over kt into q times e. This is the electric field E that I'm talking about here. Let's put everything in this expression, so it will come out to be now, which I'll do in a different color. So let's put this dou n over dou x value over here in Jn equal to 0. It will be ne mu n into electric field E equal to minus E dn. The expression for this is minus n over kt q times external field E. You rearrange the terms, it will come out to be E, so minus minus gets cancelled, ne and external field E get cancelled, everything gets cancelled. You will get dn over mu n equal to kt by q. By the way, same is true for the holes, it's dp over mu p equal to kt by q, nothing else changes. This is known as the Einstein expression. Let's try to remember that, or Einstein equation. Okay, so let's solve a couple of problems based on this very concept. So in this problem we are given that just a second, we are given the mobility, the concentration. Okay, so we are given a p-type silicon sample. So this is p silicon and we are injecting some electrons. Since it's a p-type silicon, these electrons can also be referred to as minority carriers. This is a term which will come again and again, which makes sense because here there is an excess of holes, this p-type semiconductor, this slab, then we are injecting some electrons. All right, so what we are given is that we are given, and this is the x direction, we are given dou n over dou x as 10 to the power 21 cm minus 3, and we are required to find the electron diffusion current. So this means, sorry, electron diffusion current, which is given by this expression, right? EdN, dou n over dx. So what I do know, E I know, dN I don't know. This is 10 to the power 21 cm minus 3. How do I get dN? dN I know because mobility is given and I know the Einstein expression. So dN now can be written as kT over q into mu n. Let's put this here. So Jn diffusion will come out to be 1.6 10 to the power minus 19. That's the electronic charge. Dn is kT by q into mu n. KT by q has been given as 25 millivolts into mu n, that's 1000 centimeter square per volt second into 10 to the power 21. All right, so now I need to get my calculator. So this will turn out to be 1.6 into 25 into, let's do only this. So this turning out to be 40 into, so this and this gets cancelled, into 10 to the power 2 ampere per centimeter square. So this is 4000 amperes per centimeter square, which is this option B. Okay, so this was a very straightforward problem based on the Einstein expression. We were given the mobility instead of diffusion constant, but we can derive it, right? And we are also given the gradient. So this is a very straightforward thing. Okay, so up until now, if you recall, that we have now discussed diffusion as well as drift. But please note that up until now, most of the problems that we encountered are at equilibrium. Okay, here again I'll do the same test that I talked about. So let's look at this problem. Assume the semiconductor is at room temperature. So this means temperature equal to 300 Kelvin. Characterize the band diagram as shown in the figure. This band diagram will again come to our course many times. You will see this kind of band diagram over and over again. The approximate electron density is x equal to 0 and x equal to x1 r. So we are required to find the electron density here and here, but we are given only the band diagram. Now I need you to, now in this case I need to go back to your second lecture. In that we had this kind of an expression. Okay, remember this, we had this expression, right? So now let's first solve it for x equal to 0, or let's first solve it for x equal to x1. Okay, so for x equal to x1, I'm writing it as n1. It will be ni exponential of ef minus ei. What is the value of ef here? So the value of ef and ei is the same. You can see they're coinciding. Ef is your red line, ei is your dotted line. They're coinciding here. So I can write ef minus ef over kt. This will turn out to be ni, n1. This means concentration of electrons at x equal to x1, or I'll write it at n1 at x equal to x1 is equal to ni. Ni I can assume as 10 to the power 10. This is silicon semiconductor. Okay, so n1 is this. Now let's do the same exercise for x equal to 0. Okay, for x equal to x0, let's do the same analysis. So this time I'll write n0, that's at x equal to 0, ni exponent of ef minus ei. Now please note this thing, ei is a dotted line, this is your ef. So ef minus ei, this is nothing but half the band diagram. This is eg by 2 and this also is eg by 2. That's why band diagram is, that's why band gap is eg. So ef minus ei is, in this case, is nothing but eg by 2 kt. Now if you recall the expression for ni, this is nothing but the expression for ni. Ni is exponential of eg by 2 kt. This becomes ni squared. So n0 is ni squared. This means it comes out to be 10 to the power 10 square. So 10 to the power 20 cm minus 3. So n0 at x equal to 0 is turning out to be 10 to the power 20 cm minus 3. So this is our correct option, option A. That's fine. Anyone can put the numbers. What do we understand from this? Now what do we see is that you can see that this is the bulk of the semiconductor. So this is what is called the bulk of the semiconductor. It's extending, you can say, up to very large values of x. Extends to infinity. So what you can see here is that EF is close to EC. This means it's n-type, right? It's n-type diode because EF is close to EC. But you see at this interface, right? Usually we are told that you should not dope too high. It's not doped very high because there's some gap. But here, due to some electric field, due to whatever that's not known right now, but we have bent this bend, and now the electron concentration is 10 to the power 20, which is very high. Usually we don't dope this high, but still the electron concentration at this interface here has become 10 to the power 20, which is very good, because for this is a very high concentration of electrons, and thus if we apply an external field, huge amount of current can be drawn from such a semiconductor. This is a MOSFET. We'll see this will be in your future slides, but for now this is from the band diagram. It's just how you can interpret all these things. That's the exercise here. So if you remember that much, that means the work is done. All right. Okay, so I'll pause here because then next we'll move to a slightly different topic, but I'll take a pause here. If you have any comments or questions, please feel free to ask. Okay, let's go ahead. Up until this point of time, our problems or our discussions has predominantly, not always, but in most of the cases, it's always be a semiconductor which is at equilibrium, right? Now we'll talk about semiconductor which is not at equilibrium, sorry. So first question, which equilibrium am I talking about? I keep on hearing this term equilibrium. So equilibrium is context dependent. So can anyone tell which equilibrium am I talking about here? When I say semiconductor not at equilibrium, or on the previous slides or previous sessions we have been talking about that EF is flat when the system is at equilibrium, semiconductor is at equilibrium. Which equilibrium am I talking about? Anyone? Okay, which kind of equilibrium do you know? Yeah, go ahead. Take a guess. It's fine.
Nothing external is applied
Very good. Nothing
except room temperature.
Except room temperature. Okay, nothing external is applied. Okay. Let me put it in a different manner then. Okay. So equilibrium can be of different flavors. Let's say what kind of flavors. All right. So let me just list a few. You talked about something about temperature. Let's call it thermal. Okay. We just saw that if there is a concentration gradient, the electrons and holes can flow, right? If there is some pressure difference, for instance, the wind flows due to the difference in pressure, right? There can be pressure. The pressure is different on two sides, the things flow, right? Potential energy is again one such term. But again, potential energy of what type? So here I'm talking about temperature, here I'm talking about pressure. There are some different physical entities which are constant, right? In this course, or in this context, sorry, when I'm talking about equilibrium, I'm talking about thermal equilibrium. What this means is that the temperature throughout the semiconductor, someone correctly pointed out, when I'm talking about the temperature throughout, right, is constant. Okay, it's a thermal equilibrium. All right, but there are other entities. Why it's a thermal? Why we keep it thermal? Usually, if you give something sufficient time, it will reach the ambient temperature, room temperature. In this discussion, let's say. Right. So now the question arises. Okay, one point is that this internal electric field may be present, right? Thermal equilibrium does not mean the internal electric field is absent. We also saw a nickname for this, built-in electric field. Right? It can be present. That does not mean the equilibrium is broken. Okay, we saw if the doping is non-uniform, there can be internal electric fields. Okay, but it still is at thermal equilibrium. Okay, And usually at such thermal equilibrium, we derive those expressions of n naught equal to nc to the power ec minus cf, and all those expressions we have seen in the previous classes, right? Now let's do one thing. Let's disturb this equilibrium. How do I do that? If you say change the temperature will change throughout. So you see the expression kt which is coming everywhere. So the value will change. I don't want that, right? I just want that if this is a very large if this is a large semiconductor, right? I just want something like this, that only in this portion, let's say, I want to disturb. I don't want to see the semiconductor at peace. How do I do that? Now tell me this.
Uh, give light to that semiconductor.
Okay, give light. What else?
Potential.
Potential.
Connect it to battery.
Electrical potential.
Electric field.
Yeah. So in fact, these are the two most common things that we do. You can ask why only these two, because it's relatively easier to do experiments with these kinds of things. So in fact, these are the only two things that I have written. You can apply an external electric field. So if you see, this is the block that I have, right? So let's apply a battery across this V external, and this in turn will cause an electric field E external in this. And we saw in the presence of E external, drift can happen, right? And I don't know, maybe diffusion can also happen. We'll see. I don't know yet. Another thing is that I can shine light. So the question arises, how will that change the picture? So if you recall, these are the EC and EV. If you shine light, what can happen is that this electron here will go in this here, and a hole will be left behind. So you are generating an electron hole pair. If you recall that all the expressions for NP, everything, the electron concentration, hole concentration, they will change now. If you are shining light and generating let's say electron hole pairs, what it's called. So what I mean is that the due to the shining of light, I'll tell you one more related concept to this. So what's going to happen is that effectively what you are doing, you are breaking this bond, the silicon bond, which is electrons are here, right? So and there are electrons which are roaming in the lattice. So it's silicon, it's assume 2D lattice for a simple picture. If you break this bond, these electrons will become free and hole will be generated here. So it's going to happen in addition to whatever thermal at the depending on the temperature, whatever the concentration of electron or hole there is, you are deliberately creating one more hole and one more electron. So that will add to your existing thermal electron and holes, if I can say that, right? So that's the thing. So I'm deliberately disturbing this equilibrium. Okay, and if the concentration changes, you have now seen that if the concentration changes, the concentration is different between the two sides, a diffusion can happen, like built-in electric field can come, then drift will come. So all kinds of crazy things can happen. So now whatever knowledge of we have till now of a semiconductor, it's drift and diffusion, now we are going to disturb this equilibrium. Okay, and now let's go ahead. Okay, a closely related concept to this, it's covered in much more detail in your lecture. You can go through that. I'm just doing a quick recap. It's called minority carrier diffusion equation. What is it? We'll come to that later. First, let's understand in very simple terms. Concentration can be changed by diffusion, we saw that. Drift, we also saw that. Generation, I just showed you an example that if you shine light, a bond may break and it can generate electron hole pair. So electron concentration, hole concentration can change. Secondly, if there are some electrons and holes roaming around in the lattice, they can combine. This is called recombination, right? And their concentration will decrease then. Okay, so for this discussion, let's assume external electric field is 0. So let's drop this term. Okay, the second term which we have seen is generation, right? Generation is usually given by Gn and Gp. Gn is your generation rate of electrons, Gp is of holes. This is again a table highlighting some terms which you commonly use. So N naught and P naught are thermal equilibrium. Np is after, so on your left side this is N or P, right? Some recombination will happen, but every carrier has some lifetime. This means that when it's traveling in a lattice, after a certain point of time, electron is traveling, it can find a hole and recombine. This is what called lifetime. That's denoted tau n and tau p. over here. Okay, the main point is that when we talk about carrier concentration for these kinds of problems, for these kinds of systems, we only talk about minority charge carriers. What do I mean by that? So hole in an n-type semiconductor and electron in a p-type semiconductor are minority charge carriers. You know that information. But the important question is, why are we even ignoring the majority charge carriers? I mean, it's not like that they're not present. In fact, they are in majority. So why are we so adamant on ignoring them? What what uh, what is happening in the system that makes us ignore them, right? The answer is low level injection. This means that I am injecting not a very high amount of charge carriers. So let's understand. So delta P is my excess charge, excess holes. Assume it to be n-type semiconductor, right? In an n-type semiconductor, what I am doing, I am injecting some extra holes. The delta symbol means excess electrons, excess holes. Sorry, delta P. It should be much lower than the thermal equilibrium electrons, and it's also much greater than the holes, the thermal equilibrium holes. There's also two more conditions here, which is that the electrons that I'm injecting must be much lesser than n naught. This means that, so let's assume that n naught is 10 to the power 15 for the sake of discussion. N naught is 10 to the power 15 cm minus 3, and it's silicon, so p naught will come out to be 10 to the power 5. Okay, and let's say I'm injecting excess that I'm injecting, right? Let's say I'm injecting 10 to the power 10 cm minus 3. So you can see that this delta P is much greater than P naught, right? 10 to the power 10, and it's also much lesser than N naught, correct? And similarly, let's say delta N, the excess, I'm shining light, so number of holes, excess holes and excess electrons will be the same. But this delta N is actually much lower than the background concentration, so it will not, so electrons will not play any role. I mean, their concentration is fixed at 10 to the power 15. If you add 10 to the power 10 to 10 to the power 15, it will not play a role. But if you add 10 to the power 10 to 10 to the power 5, it will play a major role. Hence, in such things, if we assume a low level injection, then majority charge carriers will not play a role. It's only the minority charge carriers that will dictate the current of the device or the concentration in the device. Okay, a similar exercise is true for the p-type semiconductor. So this I'm talking about here, and this whole analysis is for an n-type semiconductor that I'm talking about at low level injection. Okay, so for p-type semiconductor, the minority charge carriers are electrons, and their concentration has to be much lower than the background hole concentration, which is the majority in this case. And it also, the excess electrons, the excess minorities, have to be greater than their background minority concentration. So these are the things. If these conditions are satisfied, we call it low level injection, and thus in this case we can ignore the majority charge carriers, right? So this is the picture now. Okay, and so these are the, so now diffusion term I have replaced here. You can see the diffusion constant dp coming, right? Secondly, I've also replaced the generation term. You can see it's the same, gl and g, it's here. So in case of, so this symbol means p, and this means we're talking about holes here, right? We're talking about holes. In n denotes n-type semiconductor, p means the concentration of holes. So this gl in fact will be nothing but gp in our case, because we're talking about holes, and in this case it will be gn. So on the top expression is for n-type, the bottom is for p-type. You can clearly see in an n-type semiconductor I'm only talking about holes. We have established that in the previous slide. So this is, you it's better that you just keep that in mind when you're trying to approach the problems. Okay, now that's enough of the theory and the introduction part. Now let's try to solve some problems based on this. Okay, so in this problem it says that a sample of semiconductor, a sample of semiconductor has a cross sectional area of 1 centimeter square and thickness 0.1 cm. Okay, so this is some semiconductor, and during the that are generated. Okay, so what I'm doing is that I'm shining some light on it. So I'm shining some light, I'm shining some light, right? Determine the number of electron hole pair that are generated per unit volume per unit time by an absorption of 1 watt of light. Okay, so power has been given to me as 1 watt. How is power related to energy? How is power related to energy?
Time.
Time. I mean, what time?
Energy into time is equal to power.
No, power is energy.
Sorry, energy divided by
Yes,
time is equal to
yeah.
power.
So this is the so what I can write here is that let's say n h nu. Okay, n is the number of photons. This is the number of photons that are coming. H is a Planck's constant. Nu is the wavelength of the photon. This is the total energy by per unit time has been given to me as 1 watt. Okay, and this n by time, right? Let's call this let me write it again. Okay, so the input power can be n, that is the number of photons. H nu is the energy of one photon times over time. This has been given as 1 watt. This n is number of photons. N by t, now I can write it as small n photons. This I can write as 1 watt over h nu. Okay, so you put the values 6.626 10 to the power minus 34. Wavelength is given, so I can write it as c by lambda. So that's 3 into 10 to the power 8. Lambda is 630 nanometers. So okay, so from this what we can do is we can get the number of photons that are being generated. Okay, so let's just get the number first. So this will come out to be 630 divided by 6.626 divided by 3. That's coming out to be 31.7 into, that's nanometers. So that would be minus 9 and minus 8 would be minus 17, and this will turn out to be plus 17. So number of photons that is coming out to be is 13.7 per second. Second inverse, please remember that, that's second inverse. Okay, and now I want to, and this is the volume at which they are falling. So I can say that volume density of photons is equal to 31.7 into 10 to the power 17 over the area, that is 0.1 centimeter cube. This is second inverse. So this will turn out to be 3.17 into 10 to the power 19 cm minus 3 second inverse. This minus 1 will become 18, and I have taken one common from this. So this is the photons that are falling per unit volume per unit time. Okay, and it has given each photon creates one electron hole pair. So then I can write number of electrons equal to number of holes. This will be equal to 3.17 into 10 to the power 19 cm minus 3 second inverse. Why I can write this is because this is okay, this is only due to generation. I'm not talking about the background doping whatever it has. This is just due to the generation, the effect of generation, that it has created this much volume density per unit second of electrons and holes, because each photon is generating one electron hole pair. So first simply I calculate the number of photons, the absolute number of photons, then I calculated per unit second how much they are. Finally I calculate the volume density of photons per unit time, and one photon is giving rise to one electrons and one holes, and this number is directly replicated. So this is our correct option B. Okay, is it clear, or did I go too fast? Is my screen visible? Am I audible? Because my laptop is giving some problems. Am I audible?
Yes, sir.
Screen visible?
Yes, sir.
Okay, good. So let me summarize this. That in this, light is shining on a piece of semiconductor. This is some piece of semiconductor, And since light is shining, as he talked about, that some electron hole pair can be generated. So given the power of the light, we can calculate the the rate of photons that are shining on this piece of semiconductor, and from that, if we divide by volume, that we can get the volume density, its rate per unit volume per unit time. And since one photon gives one electron hole pair, this is the same. Practically, this is not true. Not every photon that you drop here on this semiconductor will give an electron hole pair. There are some many terms which are associated. Hopefully in the courses it will be covered. Some quantum efficiency, one term is there, if you are interested in looking up to that. This quantum is not related to your quantum mechanics, right? There's some term called quantum efficiency. If you are interested, you can look up this term, quantum efficiency. Okay, right. So now what's been given now is that now we know that how much is the is it is sorry, how much electron and holes have been generated, right? And we know this expression. Now we need to find what is the steady state excess carrier concentration. Again, uh, recall the word excess. Okay, this is the thing that we are interested in. All right, so what does steady state mean? Steady state means with respect to time, you have given the system sufficient amount of time that it's not varying with time. So for instance, sunlight to reach earth takes about 8 minutes, right? But at the inception of the sun, right, it would not, it would have literally taken it, the first photon would have taken 8 minutes. I don't know whether the earth was the same place or not, but you get the idea. That is, it's now achieved its steady state, that every second, the number of photons, it's consistent production from the sun, and they're consistently traveling towards the earth to reach our eyes. So that takes 8 minutes. That's the steady state. It's not changing, but it's not that it's static, it's dynamic process. So that's the steady state. It means with respect to time, it's not varying, right? This means when you talk about steady state, you can make this term go to zero. All right, so please remember that this is the term which keeps coming again and again. Steady state means it's not changing with respect to time, so this differential will go to zero. Secondly, here we are not talking about diffusion. Why? Because remember, the light was shining uniformly and the electron holes pair are generated throughout, so there is no concentration gradient, right? And I'm assuming, why you are saying that you are assuming to be holes, you can just assume it to be an n-type semiconductor. So we have established that we only talk about the minority charge carriers, so they are holes in this case. But since the holes are uniform throughout, so this also does not arise. I am assuming uniform photons. Okay, this implies no diffusion. This term went to zero due to steady state. This term went to zero due to no diffusion. Now only two terms are left, but we are still generating a large number of electrons and holes here. And if you put electrons and holes in close proximity, there is a probability that they recombine. So you see, this is the recombination term. And this is the generation that we have seen in the previous. We have established what was the value, 3.17 10 to the power 19. Okay, so I can write now the expression as minus delta Pn by tau p equal to GL. All right. So what is the excess carrier concentration, which is delta, sorry, this is minus GL. Minus and minus will get cancelled, so delta Pn will come out to be GL tau p. So this is nothing but excess hole concentration in steady state. Please remember that, in steady state, because we have already put this term to zero, right? So what is GL? GL was 3.17 into 10 to the power 19, right? That was 19, yeah. And tau p is given as 10 microseconds. 10 microseconds. So this was centimeter. This is second, so this gets cancelled. So what we get, again you see the units is cm minus 3. This turns out to be 3.17 into 10 to the power minus 5, 14. 3.17 10 to the power 14, which is this option. So now notice carefully, what was the GL? The value of GL, that means the generation or GP, was 3.17 10 to the power 19 per centimeter cube per second. But the steady state concentration is the delta Pn steady state is only 3.17 10 to the power 14 cm minus 3. Compare this number with the doping that we usually do. Usually we do doping in 10 to the power 15 to 10 to the power 16. So you can still see the delta Pn, the minority charge carriers, which is excess minority charge carriers, are still less than my n naught. Usually if this, because I'm assuming it to be an n-type semiconductor, which is n-type semiconductor assumption, and n naught is usually 10 to the 15 or 16. So 14 is still lower than that. So remember, we have talked about low level injection. So inherently this problem is taking that assumption into in the way it's formulated. It's already there. Sometimes it might not be, but the basics of it will remain the same. So it's being generated. So here the electron hole pairs in this two problems, electron hole pairs are being generated, right? But since it's uniform, there can be no diffusion. So hence the second term goes to 0. On the other hand, we are interested in steady state, so this term also goes to 0. And from this we can say in steady state the excess hole concentration is order of 10 to the power 14 cm minus 3. All right. So that's the case up until now. And please recall that I've also not taken into account the drift. So when we write these expressions, we just assume that there's no electric field that is being applied to our minority charge carriers. So that's an assumption that's been inbuilt in this. All right. Okay. So I'll take a pause here because it's the first time that we have solved such kind of problems with steady state being involved. So I'll take a pause and also generation and recombination. So if you have any doubts regarding the concepts of generation, recombination, or the origins of this expression, you may ask. No, feel free to ask. We'll take a pause.
So can you explain again how we got uniform photons? It's not mentioned directly.
Okay. So this is actually okay. So these two problems are together. This problem and this problem. All right.
Okay, sir.
I should have mentioned that. Sorry, I'm very sorry about that. I should have mentioned that. This is continued from previous problem. I'm very sorry. This is continued from previous problem where we had seen that this is if you see somewhere it was written. Just hold on a second. Yeah, uniform absorption. So this word is being used since it's uniform. So here uniform photons, and thus there can be no diffusion because the whole concentration will be the same throughout. Correct? Since it's uniform. Is it clear now?
Yes, sir. Thank you.
Okay. Yeah. Good. Okay. So that's about generation and recombination.
Sir,
Yeah. Go ahead.
sir, if there is not uniform, then diffusion current and diffusion terms also came into the picture.
Yes, they will definitely come into the picture. So what you
So
say?
how one question of non where diffusion terms come
I'll see.
in next lecture or in PDF
Okay,
anyway.
because in this problem, I think in the lectures, if you see Professor Naresh's lectures, I think it is there where some diffusion is happening. All right. Hello. So it's there. I don't think I have a problem of diffusion. Let me just check. Just a second. Yeah, there is some diffusion. Okay, so just hold on. Okay, we'll not be solving this problem. Okay, because you know the solution. I'll just try to cover it as much as I can. Just hold on a minute. We'll come to that. Okay. Is it okay? Okay, you're not audible. I'll go ahead and I'll explain what we mean. Okay,
Yes,
so
sir.
yeah, okay, thank you. So we just saw that the only the minority charge carriers diffusion is the thing that matters primarily for low level injection. Again, please, I'm repeating this. This analysis that we repeat is for low level injection. All right. So now these two are mirror problems. So you can see for n-type semiconductor, minority carrier diffusion length is, so in an n-type semiconductor, the minority charge carrier will be a hole, right? So this option cannot be there, and so this option also cannot be there, right? And so one of these is the correct. So if you know the dimension analysis, actually this is the correct option. L is the length, right? And if you know the units of dp, it's centimeter square per second, right? And tp is your tau p is your that lifetime. So centimeter square per second into second, so this will come out to be centimeters. Square root of centimeter square is centimeter. So dimension analysis says b is the correct option. We'll try to work it out. This is the expression. So when you talk about diffusion length, you again talk about steady state. So we take this term equal to 0, right? Also you assume there is no generation, so you also make this equal to 0. So note, for n-type semiconductor I'm talking about holes, hence this p term is coming. All right. So now let's try to solve this. So if you see this expression, it will become something like this: del square delta pn over del x square equal to 1 over dp tau p delta pn. I'm assuming this to be y. Then just assume this to be y. So this will become something like this: del square y by del x square over some constant, which is, I'm still repeating it, dp tau p times y. So this is a differential equation whose general solution, I don't have time to do it now, but whose general solution is of the nature of a e to the power uh, x by dp tau p plus b e to the power minus x by dp tau p. So what we do is that, since this term you can see something of exponential, this has to be dimensionless. So the denominator that you see has to have the dimensions of length, and thus we can just define this term lp as, sorry, dp tau p, which is our diffusion length. Sorry, I screwed up in the last part, just a second. So what I mean is that we define this quantity at this quantity we defined as the diffusion length. So lps dp times tau p, right? So what happens is that usually since these are, we talk about we'll see this in the next problem. We'll see that will both the terms survive. For instance, this at very large negative values, this term will blow up to be infinity, right? Then that must be 0. So depending on how you take the your coordinates, usually only one of them survive, and it's the this term, it decays. We'll see how it decays, usually the problems that we encounter in real systems. So this is the kind of expression that we see, right? Formally the definition of it is that now remember, the value of y is nothing but delta p, the excess holes, right? The excess holes. So the excess holes are decaying exponentially. So how does an exponential decay look? Let me plot this. So this is delta p on the inside. So I'm only doing the analysis here, okay? So this y is being plotted here, and this is on the x-axis. So it will do an exponential decay, something like this, right? How do you define lp? Lp is that length at which, so this is some delta p in 0, this concentration, and this concentration would be delta Pn0 divide by E, where it drops to 1 by E value. This term very frequently comes when you talk about the radioactive problems, or when you talk about the capacitor charging, where it drops to 1 by E. Hence this length is defined as the, we give it a proper name, diffusion length, minority carrier diffusion length. Now similarly, if you see for the other analysis which I'll do in green, right, again we talk about steady state, so this term goes to 0. We again don't talk about generation, and you again, if you solve this problem, right, so it will come again, the expression come out to be delta n. So this is a p-type semiconductor, so the minorities charge carriers will be electrons, right, and again it will come something like this: a e to the power x by ln plus b e to the power minus x by ln, where ln is nothing but something like this: dn tau n. Okay, so so you had asked what happens if there's a diffusion, right? That's how the profile will look, something like this in x. I'm talking about steady state profile. How will it look? It looks something like this: exponential decay, right? I had made a big assumption that GL is 0. If GL is not 0 here, then this becomes a slightly difficult differential equation to solve. This is second order differential equation. Then you have to recall your mathematical physics. There are some standard expressions that way, so you have to apply them. It's a bit involved, but essentially the idea is that if GL is 0, what I'm trying to establish here is that the decay is exponential. That's your main lesson from this. Okay, so if the diffusion is there, right, so the decay is exponential from the peak. Okay, now you can also say that what if its x is, if we want to plot it negative x, again the nature remains exponential, right? This nature is exponential, it's going to decay. All right, so the answer here would be again in this, it's, we're talking about ln, so ln would be dn tau n. So this is the correct option here, and for the first option it would be the second, which we saw from the dimensional analysis, right? This. Okay, so does that answer your question partially? I don't know who asked it, sorry about that. Does that answer your question partially, what happens in diffusion expressions?
Yes, sir.
Okay, that's good, it's good, that was the next problem itself. All right, so now we have established a bit of the theoretical concepts of it. Now let's solve a few problems just to get a hang of this expression that keeps on over and over again for us. Okay, sorry. So what we are doing here is that in a very long p-type semiconductor bar. Okay, so it says, so very long. So how do I denote very long? I start like this and I leave it indefinitely. This is going to infinity. So this is p-type silicon. All right, the cross-sectional area of 0.5 cm square, so this is the area is given, and since it's p-type, so it's doped with some acceptors. So we are given Na is 10 to the power 17, again units are in centimeter minus 3, and cross-sectional area is 0.5 cm square. So what I'm doing is that holes are injected. Okay, so it's a p-type, but I'm injecting holes. So let's say I'm injecting holes from here, because remember this is very long, so I don't know where the end is, so I'm injecting holes from here, holes injection. Okay, such that the steady state excess hole concentration, so we have to keep this term, sorry, just a second. Okay, so what's happening here is that steady state excess hole concentration is being given to us, right? Just a second. Okay, so how do I write that? Steady state excess hole concentration. So this means excess hole means delta P, and since a p-type semiconductor, subscript will always also be P. It's been given as 5 into 10 to the power 16 cm minus 3 at x equal to 0. So this is x equal to 0. Let me draw the coordinate axis with a different color. Just a sec. So this is your left edge is x equal to 0 and right side goes to infinity. Okay, so that's how my this p-type silicon bar looks like. This is all the information that means some other constants are also given. What is the whole diffusion length? LP, right? How do we get LP? Sorry, LP is given by dp times tau p. We have seen that, right? The diffusion length is given by this expression. Okay, so let's find, is tau p given to us? Yes, tau p is given to us. dp is not given to us, correct? But mu p is given, and we have seen that the Einstein relation. This is, just to recall, this is the Einstein relation. We have seen its derivation today. So let's just do that. Let's put all the so the value of dp will be mu p times kt by q times tau p, right? So mu p is 500. Everything is in centimeter, and yeah, so everything looks fine, correct. So 500. Kt by q is given as 26 milli electron volts, so that will become 26 into 10 to the power minus 3. Yeah, 26 into 10 to the power minus 3, and tau p has been given to us as 10 to the power minus 10. Okay, square root of this fellow. All right, so I'll just get my calculator. So this will be 500 times 26, that's 13,000. So okay, so the units, remember here everything is in centimeters. So the units are in centimeters because this is centimeter square, and yeah, that's the only centimeter term that we have here. So this is coming out to be 13 square root of 13 into 10 to the power 5 centimeters. So yeah,
So K is in centimeter square per volt, but you have taken KT by Q as electron volt.
oh, sorry, yeah, you're correct. This has to be, the volts and volts has to be cancelled, so there is a correct. I made a mistake. Thank you. So this E also has to come, correct. An E factor also has to come. Okay, so let's just see if everything is correct. This is mu p, kt by q is 26 milli electron volts, correct. um, Tau p is minus 10. Yeah, so this is the complete expression. So okay, no, actually there's a mistake, sorry. No, just a second. No, there's a mistake. This has to be okay. So what I mean is that if you recall those expressions, the expressions of n equal to n naught at thermal equilibrium, right? It was something like ef minus ec over kt. So this was electron volts, so kt was also electron volts. So when you do kt by q, okay, this electron gets cancelled, so units of kt are in electron volts. So kt by q should be in volts. There's a mistake here.
So that is printed wrong.
Yeah, that's wrong, because I recall that when I used to do numerical, so I just used to take 26 milli. All right, that's fine, good that you pointed it out. So square root of 13 is 3.6, so 3.6 into 10 to the power 5 centimeters. Centimeter is 10 to the power minus 2 meters. All right, so this turns out to be 0.36 micrometers. This is minus 7, you shift a 0 ahead, so this is this answer, 0.36 micrometers. Again, a very straightforward problem. We are p-type semiconductor, we are injecting some holes, and again, if you see, this is the steady state concentration that's given, but it's not required for now. Till now it's not been required, but let's just see. This is the first part of this problem. So we found the whole diffusion length. This coming out to be 0.36 micrometer. And I'll also mean, what do we mean by a very long, because ideally, if you see, your silicon is in your telephone, in your mobile phones, in your laptops, tablets, and so on, right? It's not infinitely long. They are made on those transistors are made on silicon, right? But they're not infinitely long, so we have to define it, this term, very long. I'll define in the next slide. So this is one problem. This is the second problem you see over here, right? how should I do it? Just a second, give me a minute. Can you see the presentation?
Yes, sir.
Okay, so in this problem we have established that the diffusion length was coming out to be 0.36 micron. In the previous problem like this we have seen that, right? So the next problem of next part of this problem is like this. What is a steady state hole concentration at x equal to 20 microns? Okay, so how do I do that now? So as in the, if you recall in the previous slide I had we have derived such an expression, right? And I told that, so this is your concentration. Just a second. So on your y-axis is your concentration, and on your this axis here it's your distance x, right? The distance, and x equal to 0, if you recall, was this is a concentration, and we saw that it was decaying something like this, right? Exponential. So this is the delta p0 that you see is here. Delta p0 that you see is over here at this point, and then it decays exponentially, and this is the lp is the constant that we have seen. Now so what is delta p0? Delta p0 is already given to us, the access hole, which is this 5 into 10 to the 16. So I'll simply write it as 5 into 10 to the 16. Okay, and the next term is exponential, right? And then it goes minus x at, we want to find at 20 microns, so write it as 20 divided by, it's 0.36, both are in microns, mind you. Okay, this is 20. Okay, so let me get my calculator and find out this value. Again you can see 20 is much larger than 0.36, right? So what's going to happen is that this exponential will really blow up, and it's a negative sign, so it will become really small. Let me get the, what's the actual value for this. So this is exponential of this number. Okay, so it's coming out to be around just a second, minus 20. Okay, 20 divided by 0.36, so it's going to be 55. So I take the exponential of minus 55, and that's in the order of minus 25. Okay, am I missing something? Just hold on a second. So okay, so we have to go back to the previous expression that we had. Just a second, where is that expression? Yeah, so we have to go to this expression, and then we need to figure out, sorry, dp. Yeah, so because what's happening is that this is coming out to 5 into 10 to the power 16, and this number that you see over here is coming out to be 7.5 10 to the power minus 25. Okay, this is the access hole concentration. What's it coming out to be? It will turn out to be 5 into 7.5, so it's coming out to be 3.75. 3.7 into 10 to the power minus 9 cm minus 3. This is the excess holes, mind you, right? We are talking about hole concentration. So what will the hole concentration? So hole concentration will be the background hole concentration, which is P naught, the doping, plus the excess holes at x equal to 20. P naught is same throughout because it's thermal equilibrium, right? The temperature, if you recall that we had drawn this bar, right? And from this is the x equal to 0. We are injecting holes from here. This is x equal to 0. Okay, this is p type silicon. So what we are doing is that p naught, this p naught is given to us over here, 10 to the power 17, and we are at room temperature, so we assume all of them are ionized. So p naught value is turning out to be 10 to the power 17 plus something as 10 to the power minus 9. So this will be 10 to the power 17 per centimeter cube. So this will be the correct option. So what's happening? This means that even though we are injecting 5 into 10 to the power 16 holes from this edge, but just at 20 microns, right? They are nowhere. The concentration is minus 9. Okay, that's what we mean by long semiconductor. So what it means is that, let's say you go to 10 or 10 times the length of the diffusion length. In one diffusion length, you are dropping 1 by E, right? Drop of 1 by E. Okay, when you go to let's say 10, so anything which is longer than, let's say, 10 times the length of 10 times the diffusion length, you'll define it as long. So very long implies length of semiconductor denoted by L is greater than or equal to 10 times LP, diffusion length, because at that length diffusion will not play any role. The excess charge carriers, you can see it's minus 9, it's non-existent. The concentration will only be with the background doping, which is 10 to the power 17 here. Is that clear? I'll summarize that. We are given in that we are given a p-type semiconductor, very long, right, with some background doping of 10 to the power 17 cm minus 3, and we were injecting some holes at 5 into 10 to the power 16 cm minus 3 from this edge, right? First we found out what is the diffusion length. So we saw the diffusion length is 0.36 micrometers. Then we determined that at x equal to 20, so which is somewhere over here, x equal to 20. Okay, at x equal to 20, we tried to determine that what is the concentration, the excess concentration, mind you. So this is excess. This is excess concentration of holes on the y-axis. So we saw that this is the expression, and we determined that it is coming out to be this 3 into minus 9 order. But there is already a background concentration of P naught, which is 10 to the power 17. So the total concentration will naturally be only of the background. That means that if from this understanding, we see that if you go as to many orders of diffusion length, right, what's going to happen is that your excess carrier concentration will not matter. So only when the diffusion will matter only up to a few diffusion lengths, right? In this case, let's say maybe 3 or 4 microns, that's it, because then this term will drop so badly that you will not even see anything. Please, again, this concept will come when we talk about the semiconductor devices, and we actually try to understand how they're working. This concept will come again, that after a few diffusion lengths you don't care about the excess carrier concentration. All right. So we still have a few minutes. Okay, I'll try to quickly finish because still have 7 minutes. So in this problem, we are given a bar of silicon is stored with boron. So this is silicon. Boron will mean p-type, because if you recall the periodic table, boron lies to the left of silicon, hence this is p-type silicon, right? And the concentration is given as 10 to the power 16. So Na I can write as 10 to the power 16. This is p types, so acceptor type. Okay, as exposed to light, so I'm shining light here, right? And recall that generated throughout the volume, so again it's uniform. So I have been given that generation rate is 10 to the power 20 cm minus 3 second inverse, and the recombination time lifetime has been given to us as 100 microseconds, which is this, and the intrinsic concentration is, since it's silicon, we are assuming 10 to the power 10. Approximate product of steady state electron and hole concentrations. All right, so let's do that. So steady state electron and hole concentration. So remember that the concentration will be, the electron concentration will be due to the background concentration which is there, plus the generation that we are doing, right? The generation is happening, and some of it will recombine. If you recall that expression that we have derived some time earlier, there was an expression for this, this GL times tau. Okay, so we'll use that expression directly here. GL times tau n. So what will be n naught? N naught is my background concentration. So if this is the doping, then n naught will be Ni square by Na. This comes out to be 10 to the power 4 cm minus 3. Okay, so this number turn out to be 10 to the power 4 plus GL. GL is 10 to the power 20, right? cm minus 3. And tau 1 has been given as 100. Actually, it's nothing is given, so we'll assume that the recombination time of holes as well as electrons is the same, which is 100 microseconds. So 100 into 10 to the power minus 6. So if you solve this, this will come out to be 10 to the power 4 plus that's minus 4, so 10 to the power 16 cm minus 3. And as you can clearly see, since in p-type semiconductor, right, this is coming out to be 10 to the power 16 cm minus 3, because the background concentration is very low in a p-type semiconductor, which we know. So this term, the steady state, the electrons that are being generated due to shining of light, they are at 10 to the power 16, much higher than the background concentration of electrons, right? Now what you can try to find is try to find out the value of P, which will again be P naught plus this excess delta P, which is being given by GL times tau P. So P naught, the background concentration is 10 to the power 16, we know that, and this term will again turn out to be 10 to the power 20 into 100 into 10 to the power minus 6. So this is this term not multiplied. It will turn out to be 10 to the power 16 plus 10 to the power 16 cm minus 3, turn out to be 2 into 10 to the power 16 cm minus 3. So concentration of electrons is 10 to the power 16, holes is 2 into 10 to the power 16. This is not a low level injection, mind you, because the holes that you are injecting is similar to Na. Remember that low level injection, it has to be much smaller. This is not a low level injection. And you can clearly see, if you try to find out the N into P, 10 to the power 16 into 2 into 10 to the power 16, come out 2 into 10 to the power 32. It should be Ni square for thermal equilibrium, mind you. For thermal equilibrium, it should be Ni square, which is not the case here, right? So the correct option is this. The unit shall be cm minus 6, obviously. Minus 6, yeah. So you can clearly see that the NP equal to Ni square is not valid anymore when you're shining light, right? Please take that into account. How we did this? This is just the excess. This is the excess, this term. This is excess. Excess added to background will give you total. We saw that in the table that we had made from Streetman Banerjee book, right? From that. And now we have seen that. Now we can answer this question. NP equal to Ni square is valid under steady state conditions. No, we just saw steady state conditions. So this is the steady state condition. So this, even if this goes to 0, if GL is there, right? We can, in the previous problem, it was steady state, but GL was there. NP equal to Ni square was not valid, right? So this is incorrect. Low level injection, again, even if you do low level injection, you are shining some light and there's some recombination, right? NP equal to Ni square is not valid. Electric field is absent. That doesn't matter. What if diffusion is happening and you are generating and recombining something? Again, this is not sufficient condition. The only condition when this is true is non-degenerate semiconductor in equilibrium, and that too thermal equilibrium, as someone pointed out in this class itself. So this expression is valid only for a non-degenerate. We saw what's a non-degenerate mean, right? That the level has to be 3 kT apart from the EC or EV. EF has to be 3 kT apart from EC as well as EV. Okay, and then again a similar problem, but our understanding is till now, assuming low level injection, the injected minority carrier current for extrinsic semiconductor. Let me break it down. This is a semiconductor. Let's say it's an N type extrinsic semiconductor, and we are injecting minority carrier current. So I am injecting holes. This is the that diffusion equation, that minority carrier diffusion equation that we are talking about. The same problem, and it also says low level injection. So we saw that the current is going to be, and there's no field, right? So drift cannot be there. There is no generation that's happening here. So what's going to happen if you're injecting holes here? And we saw this problem. If you inject holes on this side, right, they'll exponentially decay. So this is the delta P n over x, and this is the direction x. Let's assume x equal to 0 where you are injecting. Okay, we saw it in two of the problems. So and delta Pn is decreasing, and you can also find the diffusion current, right? What's the expression for diffusion current? If you recall that Jp diffusion is minus E dP del Pn over del x. So if the excess concentration is decreasing, is changing, you can clearly see its differential will also change, right? And from there you can clearly see it will give rise to a, so this change in concentration, we saw that when the concentration changes of a carrier, its current will also change, right? So hence the answer will be here diffusion current. Okay, and this is the expression that you can see. For instance, steady state, you don't care about this. Just give me a second, just give me a second. Yeah, sorry about that. So here you, let's say even if we ignore this, right, and we have solved this expression, this differential equation in the middle two terms, and so if you solve these two terms, right, sorry, these two terms, solve these two terms, we got this expression. And if this is a delta Pn, and you can put it here and you can get a diffusion current, right? Hence our correct answer here in this case would be D. And this is a finally similar question, where when will NP equal to Ni square satisfy? It will satisfy here because you see it's in equilibrium. EF is flat and we don't see any injection or anything. Again you see EF is flat here, so this is in equilibrium, right? It will definitely not be here. Quasi Fermi levels we'll see in the next slide, next lecture, or it might have been introduced. So we'll see that this is happens, these are quasi Fermi levels. They are introduced when we have injection. And injection, we saw that when we inject current or shine light, it's no more in equilibrium, and hence this Fermi level breaks. We take it to be broken, so as to satisfy some equations. And also you can see there is an electric field here, and EF is not flat. So EF is not flat, this is not in equilibrium. So again this is also not true. So only A and B are correct here. And finally, which of these have excess carrier generation? So we usually, I'll cover in the next class, but these the correct answer. Here you see no injection, actually no injection of shining light. Only then the splitting happens. When you have excess generation, then only the splitting happens. You can refer to the lecture slides. We'll cover in the next time also, right? So yeah, so that is all from my side. I'll stay back for a few minutes in case you have any doubts or comments. You may ask. Otherwise the session is closed. So we have already 3 minutes over time, that's fine. So I'll stay back for any comments or questions on today's session specifically, and I can even stay back if you have doubts on some previous sessions. So thank you for your time, thank you for your patience. I hope to see you next week, and I'll upload you can write to me and I'll upload this session to this YouTube channel. I'm sharing the link as well as the email ID. So I'll upload there. I'll also upload the PDF for this presentation, so you can also refer to that if you need something. Okay, then thank you. If there are no doubts, let's close this session. Thank you everyone. Goodbye.
Thank you, sir.